go. In the second part of the presentation, I wanted to talk about the inverse spin Hall effect. Spin Hall effect was the spin polarization at the edge of the material when we apply a current through the material. So a question arises here. In the inverse spin Hall effect concept, there is no applied current to the sample, but we measure DC voltage generated at the edge of the material. In order to observe this, we need to inject polarized spins into the material. In order to polarize the free electrons, they applied magnetic field to the film plane, and they excite the free electrons by exposing the circularly polarized light. And when they apply this light, the free electrons becomes movable inside the material. Because of the spin Hall effect, or because of the spin orbit coupling, or we can say inverse spin Hall effect, a DC voltage is generated at the edge of the material. So it is the first observation of inverse spin Hall effect in 1984, and they successfully measured the generated voltage at the edge of the material. And this experimental method was proposed by the first time again by the Diakonov before 1 year of this study. Later, in 1999, a paper is published by ISHE. The title was Spin Hall Effect. In his paper, he proposed an experimental method consisting the spin Hall effect and inverse spin Hall effect together. In his proposed experiment, he designed a multi-layer structure consisting a heavy metal and insulating layer and a second heavy metal. If we apply current through this material, it will be spin polarized at the edge of the material, and it will be injected into the second heavy metal. So in the case of inverse spin Hall effect, we should observe negative voltage is generated at the edge of this material. So this was the experimental method that ISHE proposed in his paper without any experiment. After 11 years, Brun et al. Experimentally demonstrated that this ISHE method is working, but it was very challenging to fabricate. They fabricate this design in the lateral case. And instead of making an insulating layer here, they removed the material and they made empty space for insulator. And when they apply current through this material, if it is spin polarized due to the spin Hall effect, it will be injected to the next line, and it will generate a negative voltage at the edge of this device. It was very challenging to fabricate this device. Because of this, it takes 11 years. Here, we know that most of the heavy metals have spin diffusion length in several nanometers, and it was very challenging to fabricate that insulating layer in the thickness of several nanometers. It becomes conductive. When you make this layer very thin, it becomes conductive. So it was very challenging. During this time period, another spin injection method has been discovered by the Azevedo et al. In 2005. In their experiment, they used permalloy, tantalum, and iron cobalt materials, a tri-layer structure. and they used a ferromagnetic resonance. Under the resonance condition, they measure the voltage created at the edge of the material. And under the resonance condition, they successfully observed a DC voltage is created, and the created voltage was depend on the RF power. When they increase the RF power, they observed more voltage is generated. For the next step, they wanted to change this type of this spacer material. Instead of tantalum, they put copper, palladium, and tungsten. And they observed this generated voltage was material dependent, and it was increasing as the atomic number increased. So this was the clear evidence for inverse spin Hall effect, but they couldn't clarify this effect in their papers. After 1 year, Saito et al. Clarified this effect by fabricating a permalloy structure on top of a platinum strip. And they did the same ferromagnetic resonance experiment, and they measured the voltage created at the edges of the material. And they swept the angle. This is the angle for applied magnetic field. If this theta is 0, it is parallel to the voltage axis. And if it is 90 degree, it is perpendicular to the voltage axis. They observed, they successfully observed resonance spectrums for at any angles. But for the theta is 0 angle, 0 degree, they could not observe any voltage is created. When the theta is 90 degree, they observe maximum voltage is created at the edge of the material. And this was the clear evidence for the inverse spin Hall effect. And the results were consistent with the prediction of inverse spin Hall effect. So this is the method that we can inject spin polarized electrons into the another material. Under the ferromagnetic resonance condition, we can inject spin polarized electrons into the next material. So we can observe inverse spin Hall effect. By using this method, later Frango et al. Tried to characterize the finite size effects of iridium manganese. In their studies, they used a reference layer without iridium manganese layer. They used permalloy, and they analyzed the resonance spectrum. They analyzed the line width of the resonance spectrum. As we know from the literature, this line width is depend on the damping parameter. If damping parameter change, this line width also change. So for the reference, they put permalloy and they measure the damping parameter as a function of temperature. And they observe the permalloy's damping parameter does not change by the temperature. But when they put iridium manganese in addition to the permalloy, they observe it becomes temperature dependent, and they observed a maximum damping parameter is enhanced to maximum when the phase transition occur. The phase transition is the transition of iridium manganese from antiferromagnetic to a paramagnetic state. So when they did experiment, thickness dependent experiment, they observed this enhancement also shifts in the temperature. So this was the very beautiful experimental method that we accurately analyze the finite size effects of antiferromagnetic materials, and we can observe the critical temperature of this element. So in the literature, there are many different type of studies based on inverse spin Hall effect, and you can find it in the literature. So I don't want to go deep into details in this topic. So I'm finishing my presentation here by summarizing the presentation. Until here, for the second part, we discussed the phenomenology of inverse spin Hall effect, and we talk about the brief history about it, and we give several applications based on the inverse spin Hall effect. That's all I wanted to talk about my presentation for Biospin Journal Club, and thanks for watching.